Warm greetings to all. I am Dr. J. Tamilmani, Assistant Professor, PG and Research Department of Mathematics, Sri Sharada College for Women, Salem. I welcome you all for this video. The main context of this video is to discuss about maximal ideal and prime ideal and the relation between these two ideals. Before we discuss the concept of maximal ideal, we just recap what is ideal. A subset A of R is called ideal if A is subgroup under addition and for every R belongs to R and A belongs to A, both RA and AR should be in A. Now we'll see what is maximal ideal. An ideal M in a ring R is a maximal ideal of R if M not equal to R, and whenever J is an ideal of R such that M contained in J, J contained in R, then either J equal to M or J is equal to R. In precisely we can say a maximal ideal is a proper ideal, that is M is not equal to R and the only ideals containing M are M and R. Now we see example for maximal ideal. Now we take the ring of integer and the ideal which is generated by 5. Now we check this ideal is a maximal ideal. It is very clear that m generated by 5 is a ideal because a ring of integer is uh, group under addition. Therefore m generated by 5 is also uh, subgroup under addition. And here if we take any element r belongs to z, then 5 times r also belongs to m. So this is clearly m generated by 5 is an ideal. Now we check whether this m is maximal ideal or not. First we have to check whether m is not equal to z. Here m is just a multiple of 5 only, but z is set of all integers. So obviously m not equal to z. The first condition of maximal ideal is satisfied. We next check the second condition. That is, we have to check whether there is any proper ideal that contains m. Here, there is no proper ideal that contains multiples of 5. Therefore, we can say that the ideal generated by 5 is a maximal ideal. Now, if we take another ideal which is multiple of 12. This is also an ideal of the ring of integer z. Now we check whether this ideal I multiple of 12 is a maximal ideal or not. First we have to check I not equal to z. Yes, here also I is just a multiple of 12 only, where z is set of all integers. So they are not equal. So the first condition is satisfied. Now we go for the second one, that is we have to check whether there is any proper ideal that contains I. Yes, here we can find an ideal that is multiple of 6 which properly contains I. So that is I properly contained in A, which is a multiple of 6. So here we could find such an ideal properly contains I, that is multiple of 12. So the second condition violates. So here we can't say this I, which is multiple of 12, is a maximal ideal. Next we see what is prime ideal. An ideal P is a prime ideal of a commutative ring R if for any element AB belongs to P implies either A belongs to P or B belongs to B. We see example for prime ideal. Again we are going to take the ring of integer and consider the ideal generated by 5. Now check this ideal is prime or not. If we take any element AB belongs to P, then either A or B must be a multiple of 5. So obviously this is a prime ideal. Now we take another ideal which is multiple of 6. Now check it is a prime or not. So if we take any element of the form AB belongs to I, that is here I am going to take 2 times 3 which is belongs to I, but here neither 2 nor 3 belongs to I. So here this I generated by 6 is not a prime ideal. The main core of this video is discuss about the relation between maximal ideal and prime ideals. A maximal ideal is a prime ideal, it is always true, but the converse is not true. Here we are going to prove a maximal ideal is a prime ideal, and also we are going to provide the counter example that prime ideal need not to be a maximal ideal. Before proving that every maximal ideal is prime ideal, now we're going to discuss some characterizations. The proof of the characterizations are not given in this video. In a commutative ring or an ideal is a maximal if and only if the quotient ring is a field. That is, if M is a maximal ideal, if and only if R by M is a field. And in another characterization, in a commutative ring with unity, an ideal is prime if and only if quotient ring is an integral domain. That is, P is a prime ideal if and only if the quotient ring Rp is an integral domain. And maximal ideals are used to develop the structure of ring and to understand the interaction between ideals. So it is very necessary to deal about maximal and prime ideals. Now we are ready to prove that every maximal ideal of R is a prime ideal. Here we have taken that R is a ring, and I'm going to take a maximal ideal. It is any maximal ideal, and we need to prove that M is prime ideal. By the characterization we have, this characterization says that M is maximal ideal if and only if R by M is a field. This gives us the quotient ring R by M is a field. And we know that every field is an integral domain. This gives us this R by M is an integral domain. The quotient ring R by M is an integral domain. Then by the another characterization which says that P is prime ideal if and only if the quotient ring is an integral domain. So here R by M is an integral domain. By this characterization we can say that this M is an principal ideal. This gives us M is a prime ideal. Thus we proved that any maximal ideal is a prime ideal. Now we going to talk about the converse part. That is, converse need not to be true. For that we are going to provide an example. Now consider the ring of and integer, the zero ideal. So here we have taken the ring of integer z and the zero ideal. Now we know that the quotient ring, this z and the zero ideal is isomorphic to z. And we know that z is an integral domain. So this gives us z by I is also an integral domain. By the characterization which states that if P is a prime ideal, that gives R by P is an integral domain. So here Z by I is an integral domain. So by this characterization we can say that the zero ideal is a prime ideal. So it is very clear that I is an, that is zero ideal is an prime ideal. Now check whether it is a maximal ideal or not. Here Z by I is not a field. This gives us I is not a maximal ideal. So here we have provided an example that uh, I is a prime ideal, but it is not a maximal ideal. So the converse need not to be true. Now we try to prove that prime ideal can be maximal ideal by imposing some condition. Now we are going to add one more condition on R. That is R is finite commutative ring. Now we are going to take prime ideal. Now we are going to prove that P is maximal ideal. So by the characterization which states that P is prime ideal if and only if the quotient ring is an integral domain. So now we have the quotient ring R by P is an integral domain. By this characterization we reached this result. Since R is finite, we know that finite integral domain is a field. So R by P is a field. This is because finite integral domain is a field. Now we reached R by P is a field. Again by the characterization which states that M is maximal ideal if and only if the quotient ring R by M is a field. Here we are having R by P is a field. So by this characterization we can say that P is a maximal ideal. So now we proved that a prime ideal is maximal ideal under the condition that the ring is finite. So I would like to summarize the discussion we done here. We proved that every maximal ideal of R is a prime ideal. The converses need not to be true. We provide an counter example, and we made a prime ideal is also maximal ideal by imposing the condition that the ring R taken is finite commutative ring. Now we see how to determine a given ideal is maximal or not. An ideal M is maximal if and only if it is not a proper subset of any other ideal of the ring. This will help us to determine the ideal is maximal or not. Another thing, if R is a commutative ring with an identity, an ideal M is maximal if and only if the quotient ring R by M is a field. This is also help us to find the maximal ideal. Now we see a few applications of maximal ideals. The concept of maximal ideal applied in many areas, especially in algebraic geometry and topology. In algebraic geometry, the maximal ideal of ring of functions are often used in algebraic geometry to study geometrical objects, whereas in the field of topology, the maximal ideals are often used to describe continuous functions from a topological space to a field. Now we see applications of maximal ideal in algebra. Especially it has many applications in ring theory and algebraic field extension. Maximal ideal play a crucial role in defining quotient rings. Given a ring R and a maximal ideal M, the quotient ring R by M is a new ring that captures essential properties of R while factoring out elements in M. This construction is fundamental in abstract algebra and has application in algebraic geometry, algebraic number theory, and coding theory. And in the field of algebraic field extension, maximal ideal plays an important role. In algebraic number theory, maximal ideal in the ring of algebraic integers of a number field are closely related to prime ideals. These ideals are used to study properties of algebraic number fields and their extensions. Maximal ideals are instrumental in providing results related to unique factorization of ideals in number. So we conclude that maximal ideal is an important concept in algebra that helps to understand the structure of ring and its invariants. Also, it has applications in branches of mathematics such as string theory, algebraic geometry, field theory, and topology. Now, this is exercise. Anyone can attempt this one. First, anyone can check for the even integers and the ideal, that is multiples of z, is maximal or not. Secondly, anyone can attempt to verify the ring of polynomials. For the ring of polynomials, the ideal generated by x is maximal or prime ideal or both. Thank you.